Good morning, everyone. This is Mr. Couple. Today I'm here with my IB Physics HL Year 1 students, and we're going to be learning about electric potential. I have Eddie and Alberto that are both here today, and I told them to be brave and ask lots of questions because this is a pretty complicated and confusing topic to understand. So we've been talking about electric fields and current, and so this kind of ties it all together. What IB wants us to be able to do is they want us to be able to solve problems involving current, potential difference, and charge. So we've already talked about current, right? That's the amount of charge that passes by a point like per second. And we've also talked about charge, right, which is that fundamental property of matter. And like electrons have it, protons have it. But what the heck is potential difference? So it turns out that potential difference is related to, it's not equal to, but it's related to energy. So whenever we have fields, whether they're gravitational fields or electric fields, anytime you have fields that are acting, we always have two quantities that we talk about in physics. We talk about potential and we talk about potential difference. And you might remember this because we had something called potential. Like where did we hear that before as it relates to energy? Do you guys remember?
Potential energy.
Potential energy, exactly. And so we discussed how, like, if you're stretching out a spring, that's potential energy. We also talked about how if you lift something off the ground, that's potential energy. So the idea of like potential is that there's some sort of a field that's going to be able to transfer energy to an object. So if you release this object, like if you lift a ball off the ground, there's a gravitational field, and when you let it go, that ball is going to fall down to the ground because the field's going to give energy to it. So what we're going to be talking about today is the energy transferred by electric fields. And so to kind of make this make more sense, like instead of it being all like weird and mysterious, I thought I'd just give you guys an example, even though this is still weird and mysterious because it's not like in your everyday life you experience charges because charges are so, microscopically small, you don't really interact with them on only at like a big human scale, but at the human scale when you touch something, you don't realize that you're actually like interacting with the electric fields created by matter within your hands. You're like thinking, oh, I'm just touching a hand. But so at a human scale, we don't really think about these ideas of like charge and electric forces and things like that. All right, so check this out. The picture shows the electric field around a large positive spherical charge. So I'm talking about this. Where is it? I'm talking about this charge here. We got this large spherical charge. So there's all this positive charge on that guy, and it's a really 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 massive amount of positive charge. So that's like the main dominant body that's acting in this box. The dotted line paths, so that's these paths here, are concentric circles that are evenly spaced. So they're evenly spaced concentric circles from that center point there. Okay. We have two charges in the field. We have Q1 and we have Q2. And so the question is, if I put these two charges, and they're going to be equal charges, so Q1 is equal to Q2, so they're both the same amount of charge. What happens if I release them from rest? Well, we know what's going to happen, right? I mean, maybe I should have you guys tell me. So what would happen to Q1 if I released it from rest in this field? What will it do?
Repel.
It's going to get repelled. In fact, since I drew it on this field line, it's going to move along that field line. What about Q2?
Also repelled.
It's going to repel as well. Hey, Kong, you're here. What's up? But what's the main difference between Q1 and Q2 as it relates to this configuration here?
Distance from the center point.
You got it. Q2 is way further away. So if we remember back to Coulomb's law, KQQ over R squared, how is the force on Q2 going to compare to the force on Q1?
Way less.
Yeah, it's going to be way less. So let me draw that as like a much smaller arrow. In fact, I think from this diagram, it looks like Q2 is 3 times further away. So it should have 1/9 as much force because of that inverse square law. So 3 squared is 9, and so it's 1/9 since it's an inverse square. So if this was F, then this would be 1/9 F. I'll just leave that up there because it makes sense. Okay, so here's my question. If we release Q1 and Q2 from these locations and we just let them go, and they're starting from rest, my question is, which charge will have a greater amount of energy transferred to it by the electric field? So we talked about in previous lessons that the electric field is what's exerting this force. So realize that when you exert a force on something, you're doing work on that thing, right? You're transferring energy to it. We talked about how work is equal to FD cosine theta. So when you push something through a distance, you do work to it. You transfer energy to it. So my question is just which charge is going to have my chair. Which charge is going to have a greater amount of energy transferred to it? What do you guys think? What are your thoughts?
Q1.
Q1? Okay, Kong, tell us what you're thinking for Q1 having more energy transferred to it.
It's closer and it'll get more energy because there's more force.
There's more force, and so if we push it harder, it will accelerate faster. And if it accelerates faster, that means it's going to reach a greater velocity, and velocity is kinetic energy. So it'll be going faster, so it'll have more energy. I mean, this is kind of weird because it's sort of the opposite of how gravity worked, right? So like if I have an object like this and I say, all right, I have two objects. One, this is object A, and then down here, this is object B. And I said, okay, which object will have more energy transferred to it when it falls? What would you guys say?
A.
A, and why?
It has more potential energy.
Right, because MGH. Now, see, what's weird is with electricity, we can set up situations where actually the greater distance is not the greater energy transfer. So let me erase this. Because in gravity it attracts, but here we have positive charges that are repelling. And so actually the fact that it's closer is actually means that it has a greater force on it. So there's going to be a greater amount of energy transferred to it. So these charges will repel. They'll fly out to infinity. And so they'll just keep going forever. But because Q1 was closer, when it travels between these 2 points, it's able to pick up more energy because it started out closer to the charge. And so we have to try to explain that in a way of understanding. I think Kong, you were on the right track. So saying that because Q1 is closer, there's a greater force on it, and so that means that there's a greater amount of work done on Q1. But the other thing to realize is that not just is there a stronger force in it because it's closer, but it also travels a greater distance. And so if you remember that work is FD, not only does it have a greater force in it, but it's also going to be able to travel a greater distance. And so both of those together allow it to have more work. So let's just try to see if we can write down our thoughts here. So we're going to say that Q1 has more energy transferred to it. And then we'll say Q1 is closer to the spherical charge. And therefore has a greater force on it. And then we'll say allowing, maybe put like a semicolon. I don't know what I want there, comma, semicolon. I know I'm not starting a new sentence. Allowing more work to be done on it by the E field, I'll say. Okay, that makes sense. So since Q1 is closer, they have the same charge. Q1 is closer, there's a much stronger force on it, and then that stronger force allows more work to be done on that charge. So it will be able to get more energy transferred to it. If we went out to infinity and we like clocked the speeds of each of these charges as they flew past us, like if we're way out here at infinity and we watch these two charges fly past and we clock their speeds, it would be obvious that Q1 would be traveling way faster than Q2. And that's because Q1 had a greater force in it, and so it was able to gain more energy from the field. You could also imagine that what if there was a charge that was an infinite distance away? So if this is infinity out here, what if I placed a charge there at infinity? Well, then that charge wouldn't feel any force at all because it'd be an infinite distance away. So that positive spherical charge there wouldn't even interact with it. And so that charge wouldn't gain any energy at all from the field. And so it makes sense to think like the closer in you are to the center charge, the more energy you can get from that central charge. That's the main concept of electric potential is like we're trying to talk about how much energy can we give to a unit of charge? How much energy can we give to a charge is sort of the way to think about it. I'll define it for you guys a little bit later, but that's basically the way to think about it. It's like how much energy can you give to a charge? We call it the potential, the electric potential. It's very similar to potential energy, but it's not the same thing. It's slightly different. You'll see why in a second. All right, here's a question. Suppose that the charge on Q was significantly larger than the charge on Q1. So what if Q2 was way bigger than Q1? So what if this is just like a ton of charge on here, like tons and tons and tons of charge on Q2, but there's only like a tiny little bit of charge on Q1? Then how would this change our answer to the question we just talked about? So what if Q2 was a much greater amount of charge? Would this change our answer to what we said for part A?
Would it need more force?
Yeah, there'd be way more force, right? Because Coulomb's law says the force between two charges isn't just dependent on the distance between them, but it also depends on the amount of charge. So if F is proportional to Q1, Q2 over R squared, I'll put a big Q here. So big Q is this guy down there. So if we have a greater charge on Q, we're going to have a much greater force on Q2. And then that's going to sort of, upset the balance of what we said before. Is like now Q2 could actually have a much larger force on it than Q1, even though it's further out. And so we have to realize that this idea of this electric potential, it doesn't just depend upon how far you are, it also depends upon how much charge there is. So this would change the answer is that the force on Q2 would now be larger than F on Q1. This would result in more work being done on Q2. So when I say work being done, what I'm really talking about is energy. And so what we're saying is like the energy that the field can transfer depends on distance and charge. So the energy a field transfers depends on distance and charge. So we don't want this. This is kind of problematic. And so having it depend on the charge that's in the field is problematic. I mean, remember when we defined the electric field, we defined it so that the charge in the field didn't matter. So I'll remind you guys what we did. So we had Coulomb's law. This was like last week, I think, when we did this. So we had Coulomb's law, which was F equals K Q1, Q2 over R squared. Actually, I'll just do it with the other technique where you say like big Q, little q. So big Q is the charge creating the field, little q is the charge in the field. And then what we said was this part here, this KQ over R squared, we're just going to call that the E field. So what we said was we don't want the electric field that this center charge is creating, we don't want it to depend upon what's in the field. We want the force to depend upon what's in the field, but we don't want the electric field. We want the electric field to be kind of like this invariant quantity that only depends upon the thing that's creating it. Well, the same thing is true for energy. If we want to say how much energy the field can give to something, we don't want the amount of charge to be messing that up. We don't want the amount of charge of the object that's in the field to be affecting that quantity. So we have to define a similar quantity for energy, and that quantity is called the electric potential. Let me know if that makes sense, because that's crazy stuff if you're a beginning student. So this is that time where you guys need to say, couple, what you just said makes no sense. Explain it better.
Can you repeat it again?
For sure. So when we talked about the electric field, we said, all right, we don't want this field. Let me like draw on this picture again. Come on, eraser work. Okay, so what we're saying is like we want when we look at this object that's creating an electric field, like this field that's being created here, we don't want the field strength to depend upon what's in the field. That wouldn't make any sense. Like why if I change the charge that's in the field, that shouldn't have any effect on the strength of the electric field that this other charge is creating. Does that make sense?
Yeah.
So it's a very similar idea. It's like we don't want the amount of charge that's on Q2 to affect the amount of energy that the field can give it. Like we want like this quantity that doesn't depend upon what you put in the field. We want this like chargeless quantity. Like we want to say, hey, this field is capable of giving this much energy per charge. So like how we said, the E field is newtons per Coulomb, we can come up with this idea that the potential, which is capital V, is going to be joules per Coulomb. So we're going to say, all right, if you're this charge, you can have this much force on you for each Coulomb of charge that you have, and the field can give you this much energy for each Coulomb of charge that you have. So this is when we're working with fields, is you just have to redefine our way of thinking about things. Is like we don't want the field, like the qualities that we describe about the field, we don't want those qualities to depend upon what's in the field, because the field is always there regardless of whether we put something in it or not. And so the idea is let's come up with these quantities called the electric field or the field strength, and let's come up with this quantity called the potential. So this is the potential, and then this is the field strength. And so we come up with these quantities called field strength and potential that don't depend upon what's in the field. They only depend upon what's creating the field. And that's why we say potential isn't actually equal to energy, just like how field strength isn't equal to force. We say it's the strength, it's the force per charge is the field strength. We say that the field potential is the energy per charge. So we have to like say, here's this quantity that doesn't depend upon how much charge is in the field. It just depends upon what created the field. Hopefully that makes sense. I mean, if it's weird, I don't know. Maybe it'll make sense when I start to throw some math into it. But that's the basic gist of the concepts. How are we feeling?
Okay. Yes.
I guess like I feel like after having explained that this is the first time in my life that I've actually understood what field strength and field potential means. Like I feel like this is the first time I've actually understood it. So thanks for making me re-explain it. Let's answer some questions to sort of check our understanding. All right, so the electric potential of a field, or the field potential, or the electric potential in this case, since it's electric field, but the electric field potential is defined as the work done per unit charge by the electric field. Let me highlight that. So the electric potential is the work done. So there's energy per unit charge. So that's joules per Coulomb, since Coulomb is the unit of charge. So it's how many joules, how much work can you do per unit of charge that you have. Which charge is located at a position of higher potential? So where would this field be able to give you more joules per Coulomb? At what location?
Closer to the.
Yep, closer. So we'd say that this region over here is a high potential. And then as you get further out from that center charge here, you get to region of low potential. So the word potential is just saying it's roughly saying how much energy you could give to something. But remember, if Q2 had a greater charge, even though it's in a region of low potential, it could still get more energy if it has more charge than Q1 at a high potential. So if Q1 is a tiny amount of charge, but a high potential, and Q2 is a big honking amount of charge at a low potential, it's possible that both these objects could get the same amount of energy transferred to them. The potential just says we don't care about what's in the field. We just want to rate, like, how much energy can the field give you based on where you're located. Whereas the amount of charge that it actually has is what's going to determine the amount of energy that it can get. The more charge, the more energy it can get. But we want this quantity that talks about the potential of the field, like what the field's capable of doing. And that's why we call it the potential. All right, so which charge is located at position of higher potential? So we're going to set Q1. Q1 is at high potential because it's closer to the central charge. Okay, so here's an interesting question. So with reference to high and low potential, outline the direction positive and negative charges move. So these positive charges that we have in this picture, they're moving away from this thing. Let me make this picture look like cleaner. Okay, so we said that this region here is high potential. And then the region out here is low potential. All right, so how are these charges moving with respect to the potential? Are they moving from low potential to high potential? Or are they moving from high potential to low potential? What are positive charges doing?
From high to low.
Positive charges move from high to low. So positive charges move from high to low. But what if you're a negative charge? What if I stuck a negative charge over here? What would it do?
It would be attracted.
Yeah, it would get attracted, which means that negative charges actually don't go from high to low. Negative charges go from
Low to high.
low to high. So negative move from low to high. So that's important to remember, is that positive charges tend to go to regions with less potential, and then negative charges tend to go to regions with more potential. Yep.
Isn't that dependable on the spherical charge?
Yes, it is. So what if this thing was negatively charged, right?
Then it'd be opposite.
Let's see. So we'd still define the potential as being high away from it. So we always base it on the positive charge. And so that's what's weird about electricity, is like everything, all the rules of electricity, all of them are based on the positive charge. So if this was a negative charge, it would flip. The high potential would go out here and the low potential would go in there, because it's always based on how a positive charge moves. Isn't that weird? But that's how we do it. Okay, now it says infer the meaning of the term electric potential difference. So when we're talking about a potential difference, well, to have a difference, what do you have to have? You have to have two different things. So if we're talking about a potential difference, we're saying, hey, if we go from this point to this point, if we took this Q1 charge and we moved it out to where Q2 is, that would be a potential difference. There's an amount of work that would need to be done on Q1 to move it to Q2. And so that work that's done per charge that's moved is called the potential difference. And this ends up being way more important than the actual potential itself. The potential difference is more important. So potential difference is defined as it's the amount of work done on a point charge to move it between 2 points. So to have a potential difference, you always have to have 2 points, like 2 places that you're looking at, and you're tracking how the energy is going to change from one point to the other, and so that represents how much work was done on the object when you moved it from one point to the other. So if our positive charge moved from Q1 to Q2, there'd be positive work done on it, right? It would gain energy because it would be repelled from that central object. But if we wanted to bring it back in, there would have to be negative work being done. It would slow down if it tried to move the other way. Like if we tried to shoot it at the sphere, it It would slow down as it approached. So that's what we really want to talk about, is like the potential difference between 2 points. That ends up being really useful to us, as we'll see on the back of this page. I just realized I'm going way too slow. It's going to be a long one, guys. I'm sorry. Maybe I won't give you a sheet of questions to make up for the time delay. All right, if we want to define this as an equation, what we say is this. We say V, that's potential difference. You often hear it also referred to as PD, potential difference, or V. Some people get lazy and call V voltage, even though it's technically called potential difference. I'm sure all of you have heard voltage before. The equation is that the voltage is equal to the work done, between 2 points. Let's just put like 1 and 2. So it's the work done between 2 points divided by the amount of charge that you're moving, because it's per unit charge. So voltage isn't the work done, it's the work done per unit of charge. Okay, so I want to show you guys this is going to be an even longer video if I do this, but what the hell, here we go. This is a picture of me touching a Van der Graaff generator. I have this in my classroom, maybe you guys have seen it. I don't know if I shocked you with it when you were in 9th grade or not, or if your 9th grade teacher shocked you with it, but I usually shock my 9th graders with this when I can. It has electric potential 100,000 volts. So when I touch my hand right there, that's 100,000 volts. How am I not dead? Thoughts, ideas?
Doesn't it go into the earth?
No, it goes into me. You can see that I have become charged because my hair is now standing up on end. Charge has flowed into me. 100,000 volts has pushed charge into me. It's transferred energy to this charge, and it's pushed the charge inside my body. How am I not dead? So what is it here that kills me? Is it the potential? Is it the work done, the energy, or is it the amount of charge? What's going to kill you?
Is it the charge?
Charge is harmless. It's the energy that those charges transfer. That's what's dangerous. So the energy that gets transferred to me is going to be equal to the voltage times the charge. So we'll call it E. So the energy that is transferred to my body is equal to V times Q. So that Q I just multiplied to the other side. All right, so what was V? Well, V was 100,000. But it turns out that the charge that's transferred to me was only like about a micro Coulomb of charge. It was only a micro Coulomb of charge. So if I do that calculation, so if I put in a micro Coulomb, that's 1 times 10 to the negative 6. Let me put the units in here. So this is joules per Coulomb times a micro Coulomb. Then you can see that the coulombs will cancel, and now I'll just have joules. So how much energy was transferred to me? Let's see. So this is negative 6. There's 1, 2, 3, 4, 5. So that's only 0.1 joules of energy that was transferred into me, which is not even noticeable. Like, that's not enough to do anything. I mean, it'll spark. Like, you'll see it go like, it'll like zap you, but it is not enough energy to kill you. So why didn't the Van der Graaff generator kill me? Because it was a high voltage. Like, this is a really, really high voltage, but it was a small, what?
Energy transfer?
Yeah, but why? Why did this number come out to be so low down here? We had a huge voltage. So what? I had 100,000 times a micro. Why did it end up being so small?
Because a micro is small. Of
Because
Oh,
it was a very small amount of charge. So this thing wasn't moving a lot of charge. Now, were it moving a lot of charge, oh yeah, it's going to kill you, like a lightning bolt. A lightning bolt will kill you. That's 300,000 volts. So, I mean, it's only 3 times more voltage than what I was touching earlier. But a lightning bolt transfers 15 coulombs of charge. So you can see when you do that calculation, energy is voltage times charge, you end up getting 300,000 volts. times 15 coulombs. And now we're talking about a ridiculous amount of energy. So let's see. So 3 times 15. What am I thinking about right now? Time? 45? Is that 45?
Yep.
So that's 4,500,000 joules of energy. What did I do wrong? Oh, this is volts is joules per coulomb. And then you can see the Coulomb constant. That's 4.5 million joules of energy transferred through a lightning bolt. And it's not because of like the high voltage. I mean, the high voltage is part of it, but just high voltage alone doesn't kill you. You also need to transfer high amounts of charge. So that's what we mean by this idea of potential. Like if you're like, danger high voltage, well, yeah, but that's only dangerous if there's a lot of charge being transferred. So if you have a high voltage and a high current, game over. But if you have a high voltage and a very small current, there's nothing to worry about. So that's the idea. All right, I'm going to go back to here now. I am way over budget on time. I'm sorry, guys. I think I'm just going to not give you I'm not going to give you a page of questions to do. This will be it. So that way I could go up to 50 minutes on this video if I don't give you guys an extra assignment to do. Okay, question 2. The picture shows a cell and a lamp. So this is in America we don't call it this, right? We don't call this a cell. What do we call this?
Battery.
Battery.
And we call it a battery. And we don't call this a lamp. Whoa, what did I just do? What the heck? How did that pop up? We don't call this a lamp. We call this, what do we call that thing?
Bulb.
Yeah, you call it a bulb. But, we're in IB physics world, so we're going to use different words here. So cell and lamp. All right, what I want to do is I want to draw 2 leads, which is a fancy way of saying wire. I want to draw 2 leads to connect the cell and the lamp such that current will flow from the cell to the lamp. So if I draw a lead, you're thinking like, all right, what do I need to do? I need to get electrons to this lamp, right? I need to get current to flow to this lamp. So you might be thinking, all right, so I just need to take a wire from here and just go to there and then connect it right there. So that's going to push negative charges, right? Because if I had like a negative charge right here, what would happen to a negative charge is right there? Well, there's negative here, so it would get pushed this way, right? Or would it? Well, electrons flow from low potential to high potential. But the problem is that there's no potential difference here. There's a potential difference across the battery, right? So you have this side you have low, and then this side you have high. Maybe sometimes when you look at stereo equipment, you'll see like one wire is red, and then the other wire is black. Have you guys ever seen that before?
Yep.
So the red wire, they usually call that like the hot wire. That's why I put height because I was thinking about hot. So the red wire is like your hot wire, that's your high potential, and then the black wire is your low potential or your ground sometimes. But the point is that if you're only connected to low, like if all you have over here is low, electrons aren't going to move. They can only move if you have a difference. So what we need to do is we need to connect the other side of the battery. We have to connect the lead from the other side as well, or from the cell. Sorry, I just called it a battery. And so now what happens is we have the high potential on this side, and then we have low potential on this side. And so then we're actually able to create a potential difference. So what ends up happening here is we have a potential difference. Oh, I didn't draw that how I wanted it to, but the point is that from here to, let me do this again. The point I'm trying to make is that from the 2 sides of the cell, when you have high potential on one side and low potential on the other, you end up getting a potential difference. And that's what we call V. And the voltage of a battery, like a D cell battery like this, is 1.5 volts, like an alkaline battery that you'd find in like a remote control on a TV or like a stereo, like a portable stereo. Like that's 1.5 volts for each one of those cells. That's why people call it voltage. It's really called potential difference, but people get lazy and just call it voltage. Same thing kind of happens with current too. Like some people call it ampage, and same thing happens with power. Some people call it wattage. But for voltage, it was very easy for people to abandon calling it potential difference because it's a pain in the butt to call it potential difference. All right, question 8 says, briefly explain why this configuration allows charge to flow through the circuit. Well, the reason this allows charge to flow is because it creates a potential difference. So we're going to say that connecting the leads across the battery terminal creates a potential difference. This is very similar to heat flow. So we say charge only flows when there's a potential difference. It's the same thing with heat. Heat flows when there's a temperature difference. And so it's kind of a similar thought process, which is what we're trying to do here is we're trying to make it kind of always be the same ideas. It's like, when you have a difference in potential, charge flows to try to equalize that. When you have a difference in temperature, heat flows to try to equalize that. And so that's kind of a similar concept that you'll see throughout physics. Is like whenever there's a gradient, which means a difference between two places, something's going to flow to sort of try to equalize those places. There's actually a law of physics that says this will always happen. It's called the second law of thermodynamics, or the law of entropy. And that was in the 9th grade curriculum, if you guys remember entropy. The other thing that's important is to remember that the potential difference is a result of the electric fields. But we kind of stopped talking about the fields themselves and instead discuss the potential difference created by the field. So remember that there is an electric field. There's an electric field in the wire, like going all the way down. I showed you guys a picture of that last time. So don't forget that it's there, but we sort of start to talk about the potential difference instead of the field, but the field is still there. Part B. The conventional current defined by Benjamin Franklin flows out of the positive terminal of the cell and into the negative terminal. On the diagram, draw and label the conventional current. Comment on how the direction of the conventional current compares to the direction of the electron current. All right, so let's draw the conventional current. So we're looking at the conventional current compared to the electron current. These are two different things, which is a total pain in the butt. And Eddie, you're gonna remember why, because what you said earlier made complete sense. Like if you flip it to negative to positive, that it should just flip it. But actually, because of this, we can't just flip it. We have to define everything based on the positive. All right, so here we go. So the conventional current flows out the positive. So the conventional current goes this way. So this is the conventional current. But if you were to stare at an electron right there, it would not be moving in the direction of the conventional current. The negative electron would be attracted towards the positive terminal. And over here, a negative electron would be repelled from the negative terminal. So the electron current actually goes in the opposite direction to the conventional current, which is a total pain in the butt for anyone who's first learning this for the first time. It can be extremely confusing. But the reason is because Benjamin Franklin decided that positive charges were the charges that flow. He thought, if remember in the mechanical universe video, he thought of it like a fluid, that like charge was this fluid that like flowed. And he thought about it as a positive fluid, that it was the positively charged fluid that flows. But it turns out that it's not the positive that flows, it's negatives that flow. But by that point, when we finally discovered that was in the early 1900s, it was the Tolman-Stewart experiment. When that was finally realized that negative charges were the charge carriers in circuits or in like free electrons, the entire field of electricity and magnetism had already been established and like set. And so we weren't going to suddenly just rewrite all the rules because of this new discovery. Like we would have had to rewritten everything. And so it was decided that it was easier to just leave it in place, that the conventional current is the direction of positive charge would move. And so we always think about current as being positive charges that move. And so the electrons that are actually moving are going the opposite way. It's kind of annoying. So we just want to make sure that we mention here that the electrons flow opposite to the conventional current. So that's why we call it the conventional current, because it's wrong. It's a convention. It was like agreed upon that we would define the current to be the direction of positive charge flows. What are your thoughts, guys?
It's a little confusing.
Isn't it?
Yeah.
So in a conventional current, the electrons go from low to high.
Let me think about it. The electrons always go from low to high, always. And so because of
Mm.
that relates back to what you're saying before. Good, that's good that you're thinking about that, Eddie. Yeah, so that's the reason why electrons always go from low to high. It's because of the way conventional current is defined. You got it. That's exactly right. Okay, question 3. This is where it starts to get a little bit weird. So I want you guys to imagine this electron, as it's like moving around this circuit. It's like moving around this circuit. I wanted to do that in blue. So the electrons are moving around this circuit. I want you guys to think about what happens. So when the electron first starts out in the battery, what happens is it actually gains energy. It gains potential energy from the battery. Like the battery kind of like fills it up with energy. So the electron has lots of energy and it gets pushed. It gets like zoom, like ejected out of the battery. We'll talk about the chemistry that causes this in a future lesson, probably be in August. So the electron gets launched out of the battery and it starts to move. Well, as soon as it launched out of the battery, it hits the lead. But the wires are designed so that the electrons can flow pretty freely through them. Like they're made of conducting materials that allow charges to flow through them pretty freely. But when the electron eventually, and so it doesn't lose any energy when it flows through the wire. But when the electron reaches the lamp has a metal filament in it. So I was trying to draw here with this thing. Like usually see them as like a little, whoops. You see them as like a little like curly thing like that. So the lamp has a filament in it, and the filament is specially designed to not allow the electron to flow through freely. The filament is designed to force the electron to lose its energy. And so what will happen is the electrons will actually end up crashing into the atoms in the filament, like the metal atoms. The electrons will crash into them and cause them to start to oscillate and vibrate more quickly. And that will result in the filament heating up and then lighting up and then releasing light. And so that's how filaments work, is they take all the energy away from the electrons that try to pass through them. All right, so we want to describe the potential difference across the leads. So if you have a wire, so this is what I'm trying to say. So if we have like a normal wire like this, then there's like very little energy loss when an electron passes through a wire. I'm trying to draw the word little. Very little E loss. So if an electron goes through a wire like this, there's very little energy loss. So then what does that mean the potential difference is? Actually, that's V. So the voltage across these two sides here is going to be, just describe it, if there's very little energy loss.
Mm.
So the E loss is the work done. So how much work is done on the electrons when they move through wire? Very little. So then what does that mean? Very little voltage.
Voltage.
Yeah, very little. Very, very low. Very low. We're going to say it's approximately 0. But when it goes through the filament, I don't want to use that. Whatever. This looks like an inductor. It's not an inductor. I'm sorry. That's another. Whatever. It's fine. This is the filament. When the electron tries to go through the filament, it's going to loses most of its energy. So then what's the potential difference across the ends of a filament? So, yep, go ahead. So if we're losing most of the energy, we're going to have,
High voltage.
yeah, high voltage. Remember, it's potential difference. It's not voltage. We're going to all make that mistake, and it's okay. But you're allowed to do that. But just don't confuse it for, because it's not, What am I trying to say? It's not voltage, it's potential difference. Volts are the unit that we use to measure it. Okay, so the point is that wires are designed so that there's very little potential difference. Like when a current flows through it, it doesn't really lose any energy. But then devices like lamps and resistors and other circuit components are designed for the electrons to lose their energy, because you want the energy to be transferred from the electrons to your device. Like if you have a television, you want the energy from those charges to go into operating your television. If you have a heater, you want the energy of the electrons to go into your heater. And so we say that the source of that energy is a potential difference. So the potential difference is transferring energy from the electrons to your device. Show that the power transferred by the lamp is given by the equation P equals IV. PIV. You might remember this equation from 9th grade. It was one of our circuits equations. Okay, so check this out. So power, let's remember this. So power is the work done per time. So power is work over time, or energy over time. You know what? I'll write it as E over T, since that's like the basic definition. But we'll say it's the work transferred per time. But here's the thing. We know what the work is because of over here. So if you solve this for work, what do you get? If we multiply both sides of this, actually I should probably just write this out over here. So potential difference is work per charge. Okay, did you guys figure out if we solve this for W, what do we get?
V times Q.
Yeah, we get V times Q. So we can substitute in the W up here for V times Q. I don't know why I put two V's divided by T. But then check this out. Something cool happens. That's Q over T. But Q over T, charge per time, that's current. You know, we used to have it as delta Q over delta T. And so then you can see that you end up with getting V times I. And so that's it. That's power equals current times voltage, or sorry, potential difference. So power is equal to current times voltage. And so we just showed it there with the mathematics of how we define everything. In fact, a lot of these quantities were defined so that this would be that easy. You know, if you think about it like nature of science, like why do we define things the way we do? It's so that it works out nicely. And we don't define it because it makes sense. We define it because it ends up resulting in an easy procedure to follow mathematically. Okay, so here's a question. The current through the lamp is 250 milliamps, and the cell has a terminal voltage of 1.5 volts. So we have this 1.5 volts, and then what we end up finding is that the current that flows through it, the conventional current, is 250 milliamperes. So now, I guess I'll put I equals 2. What we want to do from that is answer two questions. So first question, determine the energy transferred to the lamp in 1 hour. So how much energy would this lamp use in an hour of time? Well, we can find the power. So the power is going to be the current times the voltage. We know the current was 250 milliamps. I'm going to write that as 0.250, that's amps, times the voltage, which was 1.5 volts. And so that's going to give us a power of, I finally have a reason to use my calculator. So 0.25, I mean, I guess probably this could be done in your head, but I'm not that good at math. 0.25 times 1.5, so I get 0.375. And then what's the unit? What's an amp volt? What the heck? What's an amp volt? An amp times a volt. What is that? So an amp is a joule per second, and a volt is a, why did I put joule? Coulomb. Current per time. So current coulombs per second, and then a volt is a joule per coulomb. And then you can see what happens is that the coulombs cancel out, and then you get joules per second. But a joule per second is, you guys remember what a joule per second is? It's the unit of power. If you guys remembered, you would have said it by now. It's watts.
Is that yeah?
Yeah, you got it, Eddie. It's watts. So amp volts are watts. Okay, are we done yet? Nope, because this is the energy per second, but we want an hour. So if we want to figure out the total amount of energy, we would need to take that there's 0.375 joules per second, and then we'd multiply by how many seconds are in an hour, which is 60 times 60. So that's 3,600 seconds. So then the per seconds and the seconds would cancel out, and we just have to take that per second time and just multiply it by 3,600 seconds. And we'll get that it's 1,350. So this lamp, if we turned it on, if we left the circuit connected with the battery powering the lamp for an hour, it would consume 1,350 joules of energy. And that energy would be coming from within the cell. There's chemical reactions that are taking place. It usually involves like dissolving a substance. I don't know if they taught you that in chemistry, but I'm going to talk to you guys about it in an upcoming topic. So don't worry, we'll discuss battery chemistry later on. Next question. The lamp turns off after 52 hours. Why would it turn off? It's plugged in. Why would it turn off after 52 hours? What's preventing this thing from just running forever? Why does it shut off after 52 hours?
The filament.
Nope, that's not the filament. That's a good guess though. Like the filament got too hot and it like burned out. But filaments usually last for like, years, not hours.
The potential difference like got smaller
Why?
because the battery died out.
The battery dies. Yeah, the battery gets drained. So there's chemicals in the battery that are constantly creating this separation of charge. They're creating this potential difference. Eventually, the battery is going to get drained. It's going to run out. And so that's why it's dying after 52 hours. So we want to estimate the charge capacity of the cell. It looks like I really need to wrap this up. I just hit the 50-minute mark. That's ridiculous. I'm sorry, guys. The lamp turns off after 52 hours. Estimate the charge capacity of the cell. So we want to figure out how much charge is inside the cell. Well, here's what we know. We know the potential difference is the energy per charge. We can find the amount of charge by, multiplying both sides by Q and dividing both sides by V. So if we rearrange this equation, we'll find that the amount of charge is equal to the work divided by the potential difference. So I just divided multiplied Q on both sides and then divided V both sides, and I got that. Now we know how much energy this thing is going to use. So let's solve for this. So we know how much energy it's going to use. It's 52 hours times the energy that it used per hour, which was over here. So that's 1350. And then we can divide that by the potential difference of the battery, which was 1.5. And if we do this math, we can calculate, so times 52, and then divided by 1.5, we can determine that the battery has within it 46,800 coulombs of charge. So I'll call that, see how it looks like I have two sig figs. So I'll call that 4,700 or 47,000 rather. 47,000 coulombs of charge inside a battery. Now think about that for a second, guys, because that's a lot of charge that's inside a regular old like D-cell battery. Because a lightning bolt was 15 coulombs. So if I divide this by 15, that's 3,120. So like a typical lightning bolt, if you wanted to use lightning to charge a D-cell battery, it would require 3,120 lightning bolts of charge transferred into your battery to charge it up. That's a lot of charge that those batteries hold. I'm done. Sorry for the long video, guys. I hope you have a wonderful day.